This is section 5.4, homework problem number 3. In this problem, you are given a statement, and this statement is every non-negative integer power of every non-zero real number is 1. And this is the proof, and your task is to find the error in this proof. Now let's try to make sense of what the statement is saying. It says every non-negative integer power, so the power is non-negative, of every non-zero real number, so non-zero real number raised to non-negative power, this result is equal to 1. So basically this is for all n greater than or equal to 0 and r not 0. That's basically what this statement is saying. Now let's take a look at the proof. So this is let R be any non-zero real number, and let Pn be this statement R to the power n equals 1. Now there are two steps, right? The first is the basis step to show that P of 0 is true. Now here's the argument. P of 0 is true because when n is 0, r to the power 0, when r is not equal to 0, by the property of the exponent, this is equal to 1. So therefore there's no problem in this particular step. Now I do not see any problem here. Now the next is the inductive step, right? So you're going to assume Pi is true for all the integer I from 0 through k, okay? Where k is a integer greater than or equal to 0. So, and then you want to prove that P of k plus 1 is, this statement is also true. So that's the correct statement of the inductive step. You will have to do that. So therefore, let's see the proof. So let k be any integer with k greater than or equal to 0, which is good. And suppose that r to the I, where this I is any integer from 0 to k. Okay, suppose this is true, r to the I equals 1. Well, that's what we want to prove, right? So you're supposed to assume this P of I being true. So this seems to be okay. This is the inductive hypothesis, which is true. We must show that P of k plus 1 is true, which is r to the k plus 1 is equal to 1. Yep, which is what we want to prove. Now let's actually look at the proof here. So the left side of this, so this is what we want to prove, right? Let's begin with the left side. So start with the left side equals r to the k plus k and minus k minus the quantity of k minus 1. Well, the reason is supplied here. If you check the algebra, you do see that this is true, right? So there's no question about this equation. Therefore, this is equal to that. Now the next step is to use the negative exponent. When you have a negative exponent, that means it's going to be the denominator. So here, I think, let me explain. So when you see this plus sign, that means you have r to the k times r to the k. That's I see no problem here. When you minus the power of minus the quantity of k minus 1, the negative sign will bring this r to the bottom. So basically that's the division instead of the multiplication. That's why it goes to the bottom. So goes to the bottom. Let me move that here, need a little room. So r to the k minus 1. Okay, that's all according to the exponent property. So it seems that looks good. And then let's look at the next step. The next step, because we already assume r to the I equals 1 for each integer I from 0 to k. So therefore this is k. So according to the supposition, this is going to be 1. And this is also 1 for the same reason, right? Now r to the k minus 1. So is that true? Where is that from? Let's dig into here. The supposition is for any I from 0 to k, right? So the I is any number from 0, 1 to k. So any I here, r to the I will be 1. Now let's take a look at this one. R to the k, well, you know, k is, what is k? K is any integer greater than or equal to 0. So k can be any integer greater than or equal to 0. Now, what if k being 0? What if k being 0? Then in this case, here this will be r to the 0 minus 1, which is r to the 0. And this step, here in the next step, the proof, quote, the proof, okay, assumes that r to the, this is not r to the 0, sorry, r to the negative 1, right? 0 minus negative 1, which is the negative 1, negative 1. So this proof, quote again, quote proof, assumes that r to the negative 1 is equal to 1. However, I do not see that's being supposed. The supposition is for any I from 0, 1 to k, r to the I is equal to 1. Now, this is certainly not one of those numbers from 0 to k, right? So therefore, this being equal to 1, that's questionable. I do not see that in the assumption here, okay, in the supposition here. So that's something that's not quite right. So just right there from here to here, this is not true when k is equal to 0. Of course, from here to here, this seems to be right, and so I think this is the key. This is where the mistake is.